Can you see the slide on slideshow mode? Is it?
Wala ka
Yes.
slideshow, miss.
What about this?
Okay na, miss.
So we're now on areas of plain region. So last meeting we have started with this. However, I think I have missed drawing the differential element that it would be easy for you to follow through the principle applied in determining the area under the curve of the function. So we're going to go through again, but this time I'll be a little bit faster on the examples that were already covered last meeting. So we have here the learning objectives. So find the area between the curve, the x-axis, and the two given ordinates. So the area of the curve, the x-axis, and the ordinates, where the ordinates represent the limits of the integral. Or you will also find the area between a curve and the x-axis, where the ordinates are given by the points where the curve crosses the axis. So this time you'll be the one to determine the limits of the integration, which is in this case representing the points of intersection of your function with the x-axis. And the last part, you will be asked to determine the area between two functions or between two curves, or it could even be between a curve and a line. Now, we've known that when we determine or evaluate a definite integral, it's also equivalent to determining the area of the curve bounded by the limits of the integration. So the integrand here is the function. So this is our function of x, and your limits of integration are a and b, representing the lower and the upper limit. So one of the many applications actually of the definite integral is in finding the area under the curve bounded by the limits of the integral, in this case, which represents the two values of x, which are actually, in terms of geometry, represents two vertical lines, which also are boundaries, which are the boundaries of the area that is being determined. Now, so definite integrals are used to find the area between a function and the x-axis. The limits are the points of the start and the end of the area you're asked to find. And if the curve is not drawn, it is always suggested that you'll be the one to draw the curve. And this is where you're going to recall the principles that you have learned in curve sketching in your high school. So you're going to apply that in here.
Good afternoon, miss. Excuse me, miss. Ang mic mo, miss, ga sa graph, miss?
Sa graph siya.
Yes, miss.
Sa connection. Now, is it still bad? Is my microphone still bad?
Okay, miss.
Sige. Thank you. If the curve is not drawn for you, it is suggested that you be the one to draw your curve using the principles that you have learned in previously learned principles on curve sketching. Now, this is the curve that we have discussed last meeting, the first example. And actually, the curve that you have here is represented by this equation, x squared minus 6x plus 11. Now, the integral that is given here is actually representing class the differential area. And what is this particular differential area? So we'll show to you the differential area. I think I did not draw a class meeting. So the differential area is this one. It's vertical. The orientation is vertical. When we choose the differential area, it would be in such a manner that the length of the differential area will be consistent. So what do I mean with the length of the differential area being consistent? So it has to be like at any particular location in your area, in the area that is being sought. In this case, this is the yellow shaded portion. The length of this particular differential area would be the same, represented by a similar equation. So what do I mean by that? Let's represent first this differential area by y. So you could see here that its length is y and the thickness is dx. Dx in the sense that it's parallel to the x-axis, the thickness of the differential element or the differential area. Its length is this y. If you look at it, when you get the y class, it's actually the length of this differential element representing the y of the curve minus the y of this line. The y of the x-axis is y equal to 0, whereas the y of this curve will be this equation x squared minus 6x plus 11. So you can see that the formula that you are seeing here, or rather the integral expression that you are seeing here, actually represents y dx. This is the y and this is the dx. Now, it's the y of the curve minus the y of the x-axis, which is 0. So you could only see here x squared minus 6x plus 11. You are integrating it from 1 to 4. You could see the limits here. 1 to 4. It's because it starts with x equal to 1 to x equal to 4. These are the two vertical lines. So this is your x equal to 1 line, and this is your x equal to 4 line. They also serve as the boundary of this yellow shaded area. So if this differential element is summed up, just like the Riemann sum that was shown to you a while ago, from x equal to 1 to x equal to 4, you are actually determining the area of the yellow shaded portion. Now, it was discussed last meeting on how you're going to evaluate this integral. So you just use the appropriate formula or technique. Then apply the limits. That gives you 9 square units for the area of this yellow shaded portion. So your differential element or your differential area is vertical because whether I draw it here, I can draw it here. I'll draw another one in here. The representation of the y would still be consistent. So if this is dx and this is y, your y would still be the y of the curve minus the y of this line. And it's the same as in here to in here. So as much as possible, if it could be made simple without having to divide our shaded region or the area that we want to determine, we want just one differential area or differential element for the entirety of our area, the area that we want to determine. So in this case, it's vertical. Now, if it's vertical class, the way you find the y, this y, the length of your differential area or element would be the uppermost point, whatever that represents, minus the lowest point. Okay, in this case, that's your y equal to 0 line, which is your x-axis, and the uppermost point represents the point, any point on this curve x squared minus 6x plus 11. So I think this is the one that I did not draw last meeting. Okay, do you have any question? Okay, so there's none, so we'll clear the markings and we'll proceed to the next. Now, for this particular example, the same procedure we will apply. So this is your curve. This is the curve. And it's bounded by the line x equal to -1 and x equal to 1. So if I will draw these two lines, which also represents the limits of the integral, this is your x equal to -1, this is your x equal to 1. Now, if I will draw a vertical element representing the differential area, it would still be dx for its thickness and y for its length. And the y that you could see here, starting with the uppermost point minus the lower or the lowest point, that would be the y of the curve minus the y of the line. Same curve and line for C and N. Now, if it's represented here in our integral, do you know already how this integral is evaluated? It is actually this expression. So this is your y and this is your dx. This is the y of the curve minus the y of the line, x axis, which is y equal to 0. So that is why you're only seeing this. If you evaluate this expression and substitute the limits, you will still be getting the answer that you have in here. So what was not specifically written was the differential element, because there are cases wherein your differential element is horizontal. Okay, so you have that. You have any question? Okay, so I think
Yes.
so we will continue. There are 12 examples in this slide for plane areas for those who haven't yet opened it. But it is actually made available to you for weeks already. And if we cannot finish all 12 examples today, we can have the rest read, because anyway, I just made the examples lengthy, so you will have a lot to refer to, okay, and read and study. Now you must calculate where the function crosses the x-axis. So in cases wherein the limits of the integral is not given, or the boundary of the area that you are to determine is not specified, then you must calculate where the function crosses the x-axis. You calculate the area above and below the x-axis separately, and as discussed last meeting, when the area lies below the x-axis, you are to write it, or you are to write negative before it. That way it will be positive when calculated. Then you take the total area. So in this case, you have this as an example. So if you have this particular curve represented by the function of x, and if it's plotted between coordinates or ordinates a and b, you have this area A lying below the x-axis and B lying above the x-axis. So that's the purpose why you have to write negative for A, because when this is computed without the negative sign before it, it would be a negative area. There is no such thing as a negative area. The negative only represents the location of such an area. So in this case, it lies below the x-axis. So you have to place negative before it. That's it. You just separately determine these two areas. That way, you will be able to get the total area of the two by taking the sum. Let's say for this example, yes, John Vincent.
Miss, for the labeling, for example, sa A and B, miss, can that be interchanged? Like, for example, the A would be B, or amo gina siya dapat, miss?
It could even be labeled by any letter that you want, as long as you label it properly.
Oh, okay, miss.
And you have one,
Thank you, miss.
two, as long as you label it properly. That way, whoever checks your solution would know that you are determining this area and this area. So for this example, you have this function. If it's written in expanded form, it's x cubed plus x squared minus 2x. It was explained already why it's written in factored form in here. It's written that way for you to be able to use right away, equating the factors to 0. That way you can find the points, these points of intersection. So if you notice, there is no vertical line here, which acts as a boundary for these two areas. The areas in question are bounded by the points of intersection of this particular curve on the x-axis. So discussed as well last meeting is that you are to set this, the equation of your function, you are to set this to 0 because in here, all your y's are equal to 0 on the x-axis. So your y is equal to 0, so you will determine this x value. Now, how we determine these three x values or these 3 points where your curve crosses the x-axis is simple. You just equate now the factors 1 by 1 to 0. It would give you 0 as one intersection for this. It will give you -2 for this one, and it will give you 1 for this one here. And now that you have determined the points of intersection, you will have two integrals to determine or evaluate. Let's say I label this as A, and this is as B. If I will put a differential element here, which is vertical, and this is dx, its thickness, and you have y as its length. All throughout this particular area, this y will be the same. It's the y of the curve minus the y of the x-axis. Right? Now you do the same with the b. So if you use the vertical differential element, you have dx and you have y. This time, the y of the curve, or rather the y of the differential element or area, is the y of the x-axis and the y of the curve. It's the negative of this. That's the reason why you write negative. That way it will become positive. So having said a while ago, your total area will be the sum of the areas of A and B, and that would be the integral from -2 to 0 for area A, and your y here will be the y of the curve. That would be your x cubed plus x squared minus 2x dx. That's for the area here on the left side of your Cartesian plane or above the x-axis. The other area will be B. Place it here, which is on top. So this time your limit of integration or limits of integration will be from 0 to 1. Your y in this case is the y of the line minus the y of the curve, right? And the y of the curve is this one. And that would be now giving you a negative. For it not to be negative, you place here negative before it. Because without the negative sign in here, your answer for this integral will be negative. So you have negative of x cubed plus x squared minus 2x. And of course dx. Notice that you cannot add the two integrals even though, or subtract the two integrals even though you have two functions here which are similar. It's because your limits of integration are different. For the first one, you have -2 to 1. For the second one, you have 0 to 1. Okay, so if you're going to process these two integrals, you'll be getting, or you should be getting 37 over 12. I think I made you determine that already last meeting. Your answer should be 37 over 12 for the sum of the two areas. Okay. Do you have any question? Okay, so if there's none, we will continue. So we'll have here the fourth example. So same thing as example 3, you have two areas here. Area A is below the x-axis and area B is above the x-axis. Your limits of integration will be the points of intersection of this curve, x squared minus 3x in expanded form on the x-axis. So actually, your points of intersection are this, 0, this one, which is 3, and this one, which is 5. Still, if you use the vertical element, that would still be consistent to any portion of this area A. Okay, that would be the y of this line minus the y of the curve. If I'll draw another vertical element here, it would be a different story because your y in this case will be the y of the curve minus the y of the line, y equal to 0. So it would be the negative of this one. So you determine the area separately of A and B using the limits for A, which is 0 to 3, and for B, which is 3 to 5. Okay? Now let's see if it's written on the other side, what would be the corresponding answer for this. So you have this one. For 0 to 3, this is your function, x squared rather minus 3x. If you look at it, it should be the y of this line minus the y of this curve. So it should be negative, right? So if you look at the solution here, there's no negative sign that is written before it. So you see an answer which is negative. But once you consider the negative of this negative answer, then you will have something that is positive already. For B, you will have the same equation, but different set of limits. So 3 to 5 here for B and 0 to 3 for A. Still, you get the sum of the two. Okay, so just raise concerns or ask questions if you cannot follow. Or you may also inform me that I'm too fast. So finding the area between two functions. So this time we'll find the area between two functions. The functions can either be line and curve or curves. Okay? Or it could even be line, a curve, and an axis. Depends on what the problem is asking. So this is finding the remaining area when the smaller area is subtracted from the larger area. This is the long method, but there is a more straightforward manner of determining the set area, which I'm going to discuss in a little while. So integrate, substitute in the limits, and find the difference between the two. Now, as an example, you have this. Okay? You have the curve x squared minus 3x plus 5. This is the curve here, a parabola that opens upward. And you have this line, 2x plus 1, y equal to 2x plus 1. Now, actually, the area that you are to determine is the yellow shaded portion, this one. So if I will use a vertical line or a vertical differential element here, this is dx, and this would be your y. At any particular portion, your y would be the same. There is no inconsistency as to how you're going to represent the y. Your y will be the y of the line minus the y of the curve, upper minus lower portion. So that's it. Now, in here, it's similar to, it's comparable to determining the area, the bigger area. So the shape of that bigger area class is this one. That's the bigger area. This entire thing is the bigger area. You're going to subtract the smaller area. So if you're going to take this area from this, what is left is this one. But actually, what you're doing is just getting the difference of the y of the line and the y of the curve, which represents the length of this differential area or element. Now, if it's going to be represented, it's just like so this would be your limit, 1 and 4. X equal to 1 to x equal to 4. So from 1 to 4, you are to get or evaluate the integral representing the difference of the equation of the line, which is 2x plus 1. And you're going to subtract from that the y of the curve, which is x squared minus 3x plus 5. Dx. So see, it's just like the same as this one. Only that in this case, you have separately determined this integral value and the value of this integral. But it could be done just in just one setting. That way, it would be more straightforward. Okay? If you process the integral expression like this or like this separately, it will still be getting the same answer. Do you follow? That's our example 5. Okay, so if there aren't any questions, we'll proceed with the next. So in here, if I'm not mistaken, I have the example 6. Sixth example. We have to calculate the area of the segment cut from the curve y equal to x times 3 minus x by the line y equal to x. So this is your line y equal to x. You can see it in here. Just okay, this is your line y equal to x. You can see it here labeled, and this is your curve x times the quantity 3 minus x. This is the area that you're interested. So if you're going to draw an element here, it would be something like this, vertical. This is your dx and this is your y. So your y here, if I'm going to write the integral, your y will be the y of the curve minus the y of the line x. That would be the area that is shaded in green. However, if you notice class, there was no mention about these points of intersection of the line y equal to x to the line x times the quantity 3 minus x. What is only mentioned is that your curve cuts the x-axis at 0 and 3. So this is 0 and this is 3. What we're interested in is this one, the point where your line y equal to x crosses the curve x times the quantity 3 minus x. So how would you find the points of intersection of these two? So that's very easy. At the points of intersection of the line and the curve, they should have the same x and y coordinates. It's common to the two. So this point is common to the line and the curve, and this point is also common to the line and the curve. So what you're going to do, just equate the equation of the line to the equation of the curve. So you will have here x for the y, or other here y of the line equal to the y of the curve. So that would be x for the line, and for the curve you'll have 3x. I'll have it expanded minus x squared. If you simplify, you'll transfer this on the other side. You have x squared minus 2x. Transfer it in here. 0. If you factor out the x, you will have x minus 2 equal to 0. If you equate the factors one by one to 0, you will have 2 points that is represented or having the coordinates 0 and 2. So this must be x equal to 2. So they're going to have this common x coordinate for these 2 points of intersection. And you go with the rest of the process of determining the integral. So you will have here from 0 to 2. So you will have here 0 to 2, y of the curve is x, 3x minus x squared, and y of the line is x. So minus x dx. If you simplify, it would be 0 to 2. You will have negative x squared plus 2x. And you'll be able to right away determine the area of the shaded region. This is a very straightforward manner of determining the area of the gray region here. Do you get it? Any question? So, okay, so if there aren't any questions, we'll move to the next slide. Now, you can, this is the process of determining the points of intersection. So I've shown it already to you in the previous slide. And you may find the area using this particular procedure also. The area under the curve, okay, it could be like this. I'll draw to you. So in this particular procedure, you will find first the area under the curve, and you determine the area under the line, and then you subtract the two. So why is that? So if this is your illustration, the area under the curve and from 0 to 2 is this one. This is the area under the curve. This entire thing. Okay? That's the integral that you determine, the first integral that you determine. Entire thing. If you take away from this particular area, this area under the triangle or under the line, this is the area under the line, you will be left with this. So that's the reason why you get to see these two integrals here on the next slide. So the area under the curve, the limit is only from 0 to 2, not 0 to 3. And the area under the straight line, which also has limits 0 to 2. If you subtract the two, your answer will be the same as the one that I have illustrated to you a while ago. Okay, wherein you will only consider directly the area of the, this one, the area of the, this one, the gray region. Okay, you cannot see, so I'll go to the arrow. Okay, this one. Now we'll go to the next. So we go to what we call finding the areas of functions wherein the boundaries are inconsistent. So this is the time that you will decide whether you will use the vertical differential area or the horizontal differential area. I haven't yet given an example where you will be using a horizontal differential area, and I think this would be one. Okay, now if you look at the figure in A, this is figure A, the upper and the lower boundaries are not the same for the left portion of the graph as they are for the right portion. What this means is, if I'm going to write one, just going to write one vertical element here. If this is your dx and this is your y, you will have here the y of the curve or this portion in your differential element over the y of the line. Okay? If I draw another one here, it's the same thing. Y of the curve minus y of the line. However, if I'm here on the left part, you will have the y of the curve minus the y of the curve. So that is why we have here what we call inconsistent boundaries. The boundaries are not consistent if you just use the same differential element all throughout the area that you're trying to determine. So what are you going to do in this case? You either look for a differential element that will be true for all this, for the entirety of this area that you want to determine of, or you can divide it into two, just like this one. You divide it into two portions. So you have the pink portion here, and you have the blue portion here. Now, let me clear first my markings. So you have to either choose another differential element or divide the two. Now let's see if we're going to use a horizontal differential element. So this time I will draw a horizontal differential element. Okay. Now this time it would be dy for its thickness and x for its length. Right? dy for its thickness and x for its length. Now, good for this particular illustration, since you're already given the 2 points of intersection. So the coordinates of the points of intersection. So as you can see here in the area written below, you can see here that since you're using dy as the thickness, your limits will also be based on y, not x. So your y here in the lowermost part is -1, and your y here in the uppermost part is 2. Now, you are to, when you're considering the length of a horizontal differential element, it's the rightmost point minus the leftmost point. So in this case, your x will be the x of the line minus the x of the curve. Since it's the x of the line and the x of the curve, it will be now having variables in terms of y. So this is the x of your line. So your line here is actually y equal to x minus 2. And since you are interested for the x of the line, you transfer the 2 in here. So that is why you will have x equal to y plus 2. This is the x of the line. As for the x of the curve, it's already in terms of x and it's y squared. So this is the x of the curve. Just do your integration. And this is your answer. Okay. Anyway, it's so easy to integrate. Now, using the horizontal differential element did not require you to divide your area here into 2 separate portions. Like you need to find the area A sub 2 and then find the area A sub 1. Okay? Now, do you have any question here in this part? And I will explain if you have divided your area into 2 sections. Okay, I think there's none. Now, what happens if you are to divide into 2 sections? So your area 2, the one in blue, you can use the vertical differential element. Why will you use the vertical differential element? Because anyhow, your length here, which is y, and your thickness, which is dx, will be consistent all throughout this particular blue area. We'll have the y of the curve minus the y of the line. Anywhere here in the blue area, that would be true. So there won't be any inconsistencies. Whereas in here, for area 1, you can have this one. Another vertical element we have here the y of the curve minus another y of the curve. The y of the curve in this section is positive, whereas the y of the curve in this section is negative. Why is it negative? Because all the y's below the x-axis will be negative. So what would you do? Just like what we have discussed in areas below the curve, because this lower part of your A1 is below the curve, you take the negative of this y here. Okay? The negative of this y here. That way, the area that you'll be computing here will be positive, and you add it to this area on top, which is just the y of the curve minus the y of the x-axis, which is 0. So in this case, you have divided your regional area into 2 separate areas. Now, the solution will be presented to you in the next slide. Okay? Now, let me clear first my markings. So if you solve using this procedure, this is your answer. This is the solution. Oh, it's not given anymore. So that's the way. Let's check. This is this one. Okay. It's the same as the one that I have shown to you. So you'll have this area. This area is bounded by this area is bounded by this point here, which has -1, -2 for its coordinates, and this one is 5 and 4. Okay, it's written in here. So if you find the area of this one, you will have from, let's see, what was determined here. Determine the area of the enclosed area for this particular curve. This is your curve. X equal to 1/2 y squared minus 3. And for the line, this is the line. X minus 1. So this is the intersection. So if you find the area in question, that would be this area plus the pink area is the one that is being determined in here. This one. And it's using the differential dx. So meaning for this area here, you use the vertical strip. The process that is used here is the same as the one that I have illustrated in the previous example, example 6. So you have dx here and you have y. Now the y of your curve, is taken from this equation. Now this equation is actually a function of x in terms of y. So you will have to rewrite it. So you will have x, transfer the 3 here, plus 3. That is equal to 1/2 y squared. Then transfer the 2 here. You will have 2x plus 6. You have y squared. And then y will be the square root of 2x plus 6. That's the reason why you see here y equal to the square root of 2x plus 6. And you get to see here square root of 2x plus 6. But take note that upper point minus lower point. You see this? Minus, minus. Why is there a minus written before this one? Since your y here below is negative, it has to be made positive. Otherwise, your area computed will be negative. So that's the reason why you have here negative square root of 2x plus 6. Why? Again, because your y here below the x-axis, if you're going to take the square root of this expression, will be negative. So that's the reason why you have negative before it, to make this one now positive. Without the negative sign in here, it's just like you're subtracting a real subtraction, this function, the curve on top minus the curve equation at the bottom. And you're not supposed to do that because in the first place, you are to actually add this area to this area. Okay, it's not a triangle, but rather somehow like a segment or a pie. You get it? So you have the negative sign here. So this is actually for the pink area. So take note of the limit. It's negative 3. Since it's dx, it's using the x coordinate. So negative 3 to negative 1. Okay? Now, if you're going to separately determine again the area in this part, you still use the vertical element. Y of the curve minus y of the line. So this is the y of the curve and this is the y of the line. X minus 1. Your limits this time would be starting from negative 1, x negative 1 to x equal to 5. And your answer would be still 18. If you're going to determine in just one integral expression the area, it could be done this way. The one I have shown to you in the previous example. You just use the horizontal differential element. So you will have dy and this is your x. I'm sure you will agree that this one is more straightforward and less prone to error. The risk of committing an error in using the horizontal differential element is small because your solution is short. Whereas if your solution is long, of course, the probability of committing an error will also be large. Now, do you have any questions regarding example 7? So this example actually illustrates the procedure that you ought to determine here, or use rather in the same scenario in here. Okay? Same din na sila scenario, sinilain ng tugaling ang equations ng curve kag sang line. Now, This is the one that I've said that you will use the horizontal. You will use the horizontal. So this is the one that I have illustrated in the previous slide. So dy, and you have x, the x of the line, which is y plus 1, minus the x of the curve, which is 1/2 y squared minus 3. And your limits, take note, is now in terms of y. So it's from -2, see here, to 4. And you're still getting 18. Of course, this is easier than the first one where you need to consider two separate areas. So if you're so used to always use the vertical differential element, try in your given area if it could be made easier using the horizontal differential element or area. Okay, now we go to the next. Now we have area between two curves. These are not real examples, but we'll show to you how to determine the area. So the area using the vertical differential element here. So you have dx and you have y. So you have y sub 1 minus y sub 2 for the y, and you have dx. So your limits will be from A to B. This vertical element is consistent whether you're in this part of the area or in this part of the area. So you're good with that. Now you can also use horizontal. Okay, horizontal in the sense that even if you're in this region or in this section, you will still have the same x here. That would be the x sub 1 minus the x sub 2. So x sub 1 minus x sub 2, and you're using the thickness dy. And since it's dy, your limits will also be in terms of y. That would be c from the lowest point and d for the highest point. So this is just illustrating that you can either use both horizontal and vertical differential area or element in this same area, bounded by these two curves. Now, what about this one? It's the same thing. If you use the vertical, element, this is your dx and that's your y. So your area will be y dx, okay, the area of the differential element, and your y will be function of x minus g of x, function of x minus g of x. Since it's dx, so it should be having the limits a to b. That would be determining the area of this red region. Okay, pale purple, let's say pale purple. Okay, now if you have this, so when you determine the area for this one, so dx and y, you still use the principal upper minus lower point. So that would be f of x still minus g of x. Here, f of x minus g of x. Either which of the two scenarios here, the vertical differential element or area is appropriate. So f of x minus g of x bounded by x equal to a to x equal to b. So that would be your limits of integration. Okay, note that f of x comes first since f of x is the higher function. So that's what I've said, the highest point minus the lowest point. That is, the f of x is greater than g of x for all points in the required domain. Okay, now what about this? What if the two curves cross over? And you are to determine the area of the bounded by, or the area between these two curves bounded from by the coordinates A to B. So you are to determine the area between the two curves from A to B. In this case, you will have this area, this area, and this area. You have three areas to determine. So in that domain, x is greater than A and x is less than B. So meaning your limits of integration, sorry about that. Your limits of integration would be from A to B. So the curves cross over twice, therefore three separate areas need to be calculated. Noting that your g of x is greater than the function of x in region 1 and 3. Your g of x is higher than the function of x in this region 1 and 3. Otherwise, it's your function of x which is higher than g of x in region 2. So you can still use the vertical element here because that would be true for all. There would be consistencies if we use the vertical element. So in case here, in the second, you will have this point and this point. X, Y. So in here, you will have the upper curve is function of x, the lower curve is g of x. It's a different story when we'll have this, okay, for the 3, because this time, your y will be g of x minus f of x. In here, yeah, it's f of x minus g of x. Section 3 and section 1 has the same manner of determining the y. Of course, in all three sections, your limits will be different. For section 1, you will have from A to C sub 1. For section 2, that would be C sub 1. That would be C sub 1 to C sub 2. And for section 3, that would be C sub 2 to B. So 3 sections, you are to determine the area of 3 sections. Check. This is it. See, you will have g of x here, the upper curve, g of x minus f of x, limit is A to C sub 1. In the second section, you have function of x minus g of x, limit is C sub 1 to C sub 2. And in the third section, you will have g of x again minus f of x, limit is C sub 2. Now, how do you determine the points of intersection? These 2 points here, this and this. The same thing, you equate this equation with this equation. You'll be getting the common values of x. And if you substitute those x values to any of these 2 equations that you'll have, you'll find the y. And since when we speak of points of intersection, it's a pair of x and y. So first determine the x. And then once you have the x, you can choose whichever of the 2 functions here. You will substitute the x values. You will determine the y. I say any because these 2 points here is common to the 2 functions. So miski diin mo lang na i-substitute, it should give you the same value of x and y. Now, example 8. Find the area bounded by the function. So this is the one I said a while ago, that you will have a curve, you will have a line, and you have here 2 vertical lines, x equal to 1 and x equal to 3. So draw a good diagram. So this is a case wherein a diagram is not given, so you'll be the one to draw. So you draw. So this is the diagram. So this is your diagram. So this is your line y equal to x. This is your curve y equal to 4 over x. And the 2 vertical lines that's being mentioned is not drawn. So let's have an annotate. So x equal to 1. So you have a line here. X equal to 1 and 1, 2, 3, 4. This is the other line here. X equal to 4. So what is what is bounded? What is the area bounded by x equal to 1? I'll just extend the curve and extend this line. We have that. So what's the area bounded? By the line y equal to x, the two vertical lines x equal to 1 and x equal to 4, and the curve. How was the area bounded? I'm going to shade it. This is the area bounded. That's the area bounded by the curve, the line, and the two vertical lines. Okay, that's it. The importance of knowing how to do curve sketching. So what's the next thing that should be done? Note that x equal to 1 to x equal to 3 is the required domain. So you'll have here, sorry class, 3 lang gali. 1, 2, 3. Sorry. X equal to, okay, but the area is more or less the same in shape as the one that I have drawn. Okay, your required domain is from x equal to 1 to x equal to 3. So this is the area. Okay, so you have two areas. The first area is, if you're using the vertical element, the first area will be y dx, and your y will be the y of this curve minus the y of this line, dx. So meaning your boundary will be from 1 to 2. For this area, it would be the other way around. It would be the y of the line minus the y of the curve, and it will be using the intervals 2 to 3. And sorry, to set up the integrals. So this is your integrals for 1 to 2. For 1 to 2, this one. So your function of x minus the g of x. For the second one, it's the other way around. So function of x minus the g of x. In here, it's g of x minus the function of x. Your limits are different. From 1 to 2, this one is 2 to 3. And of course, the rest is very easy because it's just mathematics. Okay? It's really important is you apply mathematics to real world problem. In this case, we're determining the area between curves. So our answer will be 2.15 square units. Okay, example 9. We'll have this. See different scenarios. I'm sure you know how to do here. Your function of x is negative x squared plus 4x plus 3. And g of x is x cubed plus 7x squared minus 10x plus 5 on the interval 1 to 2. So how do you find this area? So in here, you're shown the two separate areas, the bigger area minus the smaller area. That will give you this bounded area. But it can be done straightforward. It determines an area. This is the x and you have your y. So the y of the function of x, that's negative. Okay, this is your function of x. This is your function of x. this is your function of x, this curve, and this is your g of x. So you could see you have here function of x minus g of x on the using the limits 1 to 2. So this is just the two areas that we need to separately determine. That is, if you want to determine the separately and subtract the smaller area from the bigger area. If you do that, the procedure that I've shown here in the left is the same. Okay, so you could see it in here. Take function of x minus g of x. This is the more straightforward manner. You have this answer, 49/12 square units. Mostly class of the examples here are just using power formula. Now, this one, example 10, it's the same. You use the vertical differential element. Have one here, and you have one here. Now, this is your function of x. This is your g of x. So in this part, it would be function of x minus g of x for your y. In this part, you will have g of x minus function of x for your y. Now, you need to find the points of intersection. So just like what I have mentioned a while ago, finding the point of intersection simply requires that you equate the two equations. So it was equated, and you have this value. Now, you will be getting two values here, class. So, your interval is very important that you take note of. The interval is 0 to 1. But you'll be getting two values here. So, what are the two values that you'll be getting? Can you please compute? 5 plus square root of 15 over 2. The other one is 5 minus square root of 15 over 2. So you will have 4.436. The other one
0.56 miss.
you will have the other one, if it's subtraction, oh, it's 5. Point 563. So which of the two will you use? Since you are to determine the area on the interval 0 to 1 bounded by these two functions. So this is where you're going to do validation. You cannot use this one. You can only use this one because this one is out of range already. It's in here after 1. But the 0.5635 is between the interval 0 to 1. So this is the x that you will be using for the for this point of intersection, not the 4.436. You get it? So amo na siyang gamiton ang 0.5635, not the 4.436. Now, once you have that point of intersection chosen, you choose the appropriate point of intersection, especially the x, then you can determine already. So you have the two functions here. Upper function of x is x squared minus 6x plus 5, this one. And you have this for the first. And of course, you still have to determine the second one. Okay. And for the second one, is the other way around. This one comes first, subtract this one. Okay, limits is 0 to a, which is the 0.56 something, and then this is 0.56 something to 1. You'll be getting this area. for these two regions, for this one and this one. Okay? Now, the last two examples here, class, actually is similar to the one that I have shown to you, wherein you are to determine the areas of three different sections. So you have one section here, two section here, three section. Now, the first thing that you ought to do for this 11th example is determine this. So you determine this point of intersection, the coordinates, because you will have three integrals here. The first integral for this area, the second integral for this area, and the third for this area. And these are the integrals. So this is for the first, this is for the second, and this is for the third. Okay, then you just take the sum of the areas. You're still allowed to use the vertical element because for any of these areas or section, the vertical differential element will be consistent in terms of its length. So, hindi mo siya naglain, or hindi siya different. So, pwede ka kagamit vertical differential element. So, you'll have for the first one, 2x squared plus 10 minus 4x plus 16. For the second one, you will have 4x plus 16 minus 2x squared plus 10. For the third one, you will have 2x squared. This one is red. 2x squared plus 10 minus the line, which is 4x plus 16, which is this. Your limits are also different. So this is from -2 to -1, -1 to 3, and then 3 to 5. This will be the area. Okay, I think you have already enough examples. We'll have the last in here for the area topic. And this one is comparable to the pink area that I have shown to you a while ago. I just place it in here because this time your function is not just polynomial in nature like x and y only, but it's trigonometric. But still, it's no worries because you know how to integrate man, cosine, and sine. So the upper red curve is cosine of x, the lower curve is sine of x. So for this area, it's cosine of x minus sine of x. For the area on the right, you will have sine of x minus cosine of x. The limits of integration, of course, will be different. For the first one, it's 0 to pi over 4. This one, the x here is pi over 4. Let's see. 0 to pi over 4. For the second is pi over 4 to pi over 2. Okay, and then integrate and substitute the limits. Okay, do you have any questions? So the key always in correctly determining the area bounded by functions or bounded by a function, an x-axis, or a specified interval is that, number one, you should know the limits. If the limits are not given, the limits that you're going to use in your integration, you have to determine it by finding the points of intersection. And then once you have that particular point of intersection, very important as well is determining the appropriate differential area. So it could be horizontal, it could be vertical, as long as it's consistent for the bounded region. I'm referring to the length of your differential element, then you can use any of the two. But even if, let's say, for example, you already chose a vertical differential element, it's not consistent. You chose a horizontal differential element, it's not consistent. Then maybe there's a need for you to divide your region. That way, you can use an appropriate differential element that will not be inconsistent in the divided regions already. Then you just need to add the areas of the two regions, or the regions that resulted from your dividing the original area. Okay? Any questions?